Okay, here we are for me the second time doing this lecture. I just finished this lecture and went to stop the recording and I'd never started it. Happens sometimes. So this is going to actually be a really short lecture, in particular because the Intermediate Algebra Committee, of which I am on this semester, are rewriting the objectives, what we need to cover in this course. And this particular chapter, 7.6, is getting whittled down quite a bit. So we're only going to be solving equations that contain radical expressions that lead to linear equations. Now I'll actually do one for you that leads to a nonlinear equation, a quadratic equation. But for right now, this is all we're going to do. And I cannot remember if the Pythagorean Theorem is going to be part of it either. We have one question at the very end that has to do with Pythagorean Theorem, and I rather suspect that it might be on there because this is something that we also teach in developmental math, but it's really simple. So here is the major insight for this particular lecture. It's called the power rule. If I have an equation, and an equation has an equal sign, and there's something on each side of the equal sign, if I raise both sides of the equal sign to any power, then all of the solutions that make the original equation true will also be contained in any solution to the transformed equation. The transformed equation is the one that results from raising both sides to a power. Now this is the rub. What that means is we have both the original solution and perhaps extra solutions. So the possibility of getting extra solutions means that when we get to the end, we always have to check. So we'll go through the steps. So the general steps, here's my original equation. So this is 1. I have 2x minus 3 is equal to 9. So the procedure here is we want to isolate the radical part. And in this case, by isolate, we want it on one side. It needs to be on one side. And that's already given to us here. And then our next step is to raise both sides to the index of the radical. So here, first step has already been done. So, and this is my original equation. So for the second step, my index is unwritten, but it's equal to 2. So by raising both sides to the index of the radical, it removes the radical sign. And that's exactly what we wanted. And 9 squared is equal to 81. So now I just solved this really easy linear equation. And that gives me x is equal to 42. So this is not necessarily my answer. This is a possible answer. Is the original may not have an actual answer. So let's go back up to the original equation and let's see if it works. So to check it out, all you do is you start with the left-hand side, or the side with the radical. 2 times 42 minus 3. And all you want to do is see if it's actually equal to 9. I don't have to worry about the 9. I can leave that there by itself. Just keep it in my memory. So that is 2 times 42 is 84. minus 3. And that's the square root of 81. And the square root of 81 is equal to 9. So this is the solution. Now for our next example, I just want to show you, this is not one that I intended you to do, and I've tried to remove those from your homework. Although I don't mind you doing them on your homework because they're not bad, but they won't be something that you'll be tested on. So this one actually is going to lead to a quadratic equation. So I want to go ahead and go through it. I did not purposely leave any of these on the homework, but I may have missed them. So this is minus 10x minus 1 plus 3x is equal to 0. So the first thing we have to do, so this is our original equation. So the first thing we have to do is isolate the radical. It has to be on one side of the equation all by itself. So that means I need to move 3x to the other side. That becomes minus 3x. And then the next thing I need to do is get rid of the radical by raising both sides to the index of the radical, which is 2. So that results in minus 10x minus 1 is equal to 9x squared. So how do I solve this particular problem? The only game you have in town right now is by factoring. So I need one side set equal to 0. I like the leading coefficient of my degree 2 term to be 9. So I'm moving the minus 2x over, minus 10x over. It becomes plus 10x. And I'm moving the minus 1 over, and it becomes plus 1. And let's see if we can factor that. Again, we're going to just use my quick method. The method I taught you is purposely given to you because it's the method I use myself. If you want, you could check to see if this is a perfect square trinomial. It isn't. But notice, since our constant term is 1, the only things that multiply to it is 1 times 1 or minus 1 times minus 1. And we don't want to use minus 1 times minus 1 because 10x is positive. And let's just do the obvious up here. 9x times x. So let's do our check. This is what I saw on the last test. You would use this procedure, but you had forgot to do the check. 9x times, that's supposed to be not 9, but x. So I'm supposed to write there. There. 9x times x is 9x squared. 1 times 1 is 1. So now let's do the column multiplication. 9x times 1 is 9x, and this is a plus. X times 1 is x. 9x plus x is 10x. So that gives me my factorization. Now the only thing you have to remember is go kitty corner for my factorization. One factor is 9x plus 1. I'm hitting something here. 9x plus 1. The other factor is x plus 1. So if 0 is equal to 9x plus 1 times x plus 1, that means 9x plus 1 is equal to 0, or x plus 1 is equal to 0. This top implies that x is equal to minus 1/9. And the bottom implies x is equal to minus 1. So again, these are my two possible solutions. And what you have to do, I'm not going to do it, you have to take each one of these solutions and plug it in any of the equations that occur before we do the squaring. So you could plug it into the first one or to the second one. As long as your steps leading from the first to the second are valid, it doesn't matter. So you might want to plug it into the first and check to see if you get 0. And as it turns out, if you want to do that, according to my notes, that both -1/9 and -1 is a solution. But that's all I'm going to do from that one. Not going to go any further detail, because it's a radical equation that leads to a quadratic equation, and we're going to start focusing only on radical equations that lead to linear equations. And this next one is one such equation. So this is example 3. Not 3a, just plain old 3. So this deals with the cube root of x plus 1. Notice that 5 is not underneath the radical sign. That's a common error students make. Make sure you know what's under the radical. X plus 1 is under the radical. 5 isn't. Is equal to 3. So our first step is going to be to isolate the radical all by itself. And I'm going to do that by subtracting 5 from both sides. So that gives me the cube root of x plus 1 is equal to -2. And here is the squaring step. So the cube root, not the squaring step, rather the cubing step, x plus 1. So I raise both sides to the exact power as indicated by the index of the radical. Notice over here my base is -2. So -2 is what is cubed. Now, cubing a cube root removes the radical symbol. So I get x plus 1. Great, much better, right? And -2 cubed is -2 times -2, which is 4, times -2, which is -8. So, subtracting 1 from both sides, I get x is equal to -9. So this is my tentative solution. I have to go back up and I have to check. So here's my original. So let's plug in x is equal to -9. So I have the cube root of -9 plus 1 plus 5, and I want to see if that is equal to 3. Well, the cube root of -9 plus 1 is the cube root of 8 plus 5. Well, 8 is equal to -2 cubed. And the cube root of -2 cubed, by definition, is -2. -2 plus 5 indeed equals 3, and that's what we wanted it to be. So x equals 9 is the solution. We're not going to do this one because this one will lead to a quadratic equation. What I will do really fast is to show you what it will lead to. So we already have, I won't solve it, but it won't hurt you to see it. We won't solve it. So if you observe, the index is 2 of this radical. So all I have to do is square both sides. So that gives me 4 minus x is equal to x minus 2 squared, which is x squared minus 4x plus 4. And then what you would do is you would go about solving. So minus x becomes plus x. So minus 4x plus x is minus 3x. And plus 4 minus 4 is 0. It's really actually easy. So my possible answers are x is equal to 0 and x is equal to 3. And what you would want to do is go plug them in the original equation, the one that I'd written down before I squared it, and see if it would work. So really, a lot of these examples that lead to, that one also is one we won't do, that lead to quadratic equations are pretty easy. But I think literally my own self, before the committee even decided on this, I went through and I changed a lot of the problems because the instructor has an enormous amount of discretion as to what you actually learn, even from amongst the necessary topics. Which ones of those do I cover? So I'm actually going to look at using the Pythagorean Theorem, mostly because I can't remember if it's going to be covered or not, and it's so simple that it's easy to cover. So the Pythagorean Theorem is a beautiful theorem. By looking at tablets, cuneiform, of the Babylonians, they have huge tables of numbers a, b, and c, so that if you square a squared and then you squared b squared and you add them together, you get c squared. So we have robust and enormous amount of evidence to know that the ancients knew about the Pythagorean Theorem for at least 3,000 years before the Common Era. So this is something that literally goes back. So I'm going to let A represent the length of one side of my right triangle, and B represent the length of the other. So you have three sides of a triangle, always triangle. 3 angles implies 3 sides. So the sides that are adjacent to the right triangle, so this square right here is what indicates to you that this is indeed a right triangle, they're called the legs. And the longest side, which I'm going to label as C, is called the hypotenuse. And that's, I can look at the roots right there, and I know that's a Greek word. And I took classical Greek for 3 years, but hupo I do know, it means over. But the other part I can't decipher. So we're going to use this, and the Pythagorean Theorem is if you have a right triangle with legs A and B and hypotenuse C, then the following hold. A squared, when I add up the sides, the lengths of the sides squared, I get C squared. And you can't imagine how profoundly useful that is in mathematics. So let's look at this problem. Find the length of the unknown leg of a right triangle. That's misspelled, we can live. If the length of one leg is 4 meters and the length of the hypotenuse is 10 meters. So let's do this. So the hypotenuse length is equal to 10. And I'm going to say the length of our known leg, I'm going to say our known leg is going to be B. So I'm going to say that's 4. And our unknown length is going to be A. You could relabel it as X if you wanted to. So that gives me A squared. B is 4 squared. B is 4, so that's 4 squared. And C is 10 squared. So all we do now is we solve this equation. So let's go ahead and isolate. You can do this any way you want. I'm going to isolate my unknown, which is my A squared, by subtracting 4 squared from both sides. So that gives me A squared is equal to 100 minus 16. So that means A squared is equal to 84. So now we're going to do the reverse. I'm going to take the square root of both sides. And when I do that, because the index is even, then a is equal to plus or minus the square root of 84. I have two possible solutions. But these solutions deal with length. And length is always greater than 0. If you want to say a 0 length exists, then it's greater than or equal to 0. So that means for this particular problem, all I have to do is deal with the positive value. And when we refer to the positive value, we don't write the positive, we just write the square root. So is there anything else left to be done? Well, you don't know the value, and I don't care about the actual decimal approximation. What we want to do is use techniques to simplify this radical as much as we can. So let's factor 84. Let's divide it by 2. That's going to be 42. 8 divided by 2 is 4. 4 divided by 2 is 2. 42 divided by 2 is 21. 21 is divisible by 3. And 21 divided by 3 is 7. So right here are all of my prime factors. So 84 is equal to 2 factors of 2. So that's 2 times 2, that's 2 squared, times 3 times 7. So a is equal to the square root of 2 squared times 3 times 7, which I'm going to write as 21. So since my index is unwritten, but it's equal to 2, and the exponent to this 2 is divisible by 2, that gives me a is equal to, I can bring the 2 squared out. It's divided by the index times what's left behind, which is my 21. So my final answer is a is equal to 2 raised to the first power is 2 times the square root of 21. Now, of course, in the real world, if you really needed a length, like you were measuring a board to be cut, you'd bring up your trusty calculator and you would just go at this step right here, and you would find out, it's locked up on me. I tried to start 2 instances. You would just use your calculator to find out what the square root of 84 is. So in this particular case, I'd use this button. You clear it. It's locked up on me. Y'all can do it at home. So that's it for 7.6. For once, a really short and sweet lecture.